My name is Abhay Deshpande, and I'm excited to share our work from the University of Washington, Data-Efficient Behavior Cloning for Fine Manipulation via Continuity-based Corrective Labels. Our project investigates how behavior cloning can be made more efficient and practical in real-world fine manipulation tasks. Using chopsticks to pick up a coin and insert it into a piggy bank requires a high level of dexterity and precision, which would normally require an intractable amount of data. We show, however, that by exploiting local continuity in the environment, this behavior becomes possible with realistic amounts of expert data. Previous work introduced the algorithm CCIL, but it remained to show that its methodology and underlying assumptions applied in the real world, particularly to challenging manipulation tasks. In this project, we extensively validate it in multiple real-world fine manipulation tasks of varying difficulty. Specifically, we focus on grasping a very small cube, inserting a gear into a mechanism with a gap of less than a millimeter, and picking up a coin only 3 millimeters thick. We further extend this algorithm and show that it substantially improves the performance of behavior cloning in low data regimes and increases robustness to external disturbances as well. First, let's make our problem setting a little bit more explicit. We are focusing on offline imitation learning, where we are given a set of expert demonstrations and nothing else. We don't know the environment dynamics, nor can we sample from it, and we can't query the expert for labels. A significant problem in this setting is covariate shift, where as the policy acts in an environment, error accumulates and pushes it outside of the data support of expert demonstrations. Once the policy leaves the expert data support, it starts making arbitrarily incorrect actions, resulting in failure. This is illustrated on the bottom, where we see the expert and policy trajectories in black and gray respectively. Although they start in the same position, the policy slowly accumulates error and drifts away from the black expert trajectory until it's very far away. Let's go a bit more into depth on what covariate shift means. Here's a simple inverted pendulum task, and let's watch an expert demonstration. The expert's trajectory through the state space is visualized on the right, and note that it settles and stops at the upright position, or an angle of pi. Now, let's watch an imitator policy's rollout. Although the imitator is roughly following the expert demonstration, it's making small mistakes that add up over time and result in it swinging very far away from the demonstration and failing to complete the task. So, how can we combat covariate shift? Previous work has explored multiple methods, such as querying an expert for labels or using a known dynamics model to plan in the environment. These, however, require substantial additional assumptions which may be difficult to fulfill in the real world. This is where CCIL, or Continuity-based Corrective Labels for Imitation Learning, comes in, published in ICLR earlier this year. If we add a very minimal additional assumption on local continuity of the environment dynamics, common in a lot of control literature, we can generate synthetic corrective labels to augment our dataset. These labels serve to expand the data support of the expert demonstrations. Intuitively, when the policy starts to leave the data support of the expert, these labels will guide it back. The fundamental problem of covariate shift is that we know what to do near the expert demonstrations, but not anywhere else. Therefore, CCIL focuses on ensuring that policies avoid leaving the support of expert data in the first place. Essentially, the synthetic labels form a tube around expert demonstrations, thereby increasing the data support. So whereas before, the imitator would slowly drift away from the expert demonstrations, the newly generated tube pictured on the bottom expands the data coverage, resulting in more robust performance. The use of continuity is key here. It allows us to formally prove that our synthetic labels are approximately correct under the ground truth dynamics, grounding them in the real world. For example, it protects us from generating labels that say a pendulum swings against gravity instead of towards it. At a high level, the CCI algorithm is as follows. First, we train a dynamics model on the provided demonstrations, so for example, learning how the pendulum swings. Note that the learned model is only trustworthy near these demonstrations since we don't have dense data support over the state space. We then use this model to generate corrective labels with provably bounded error. There are multiple label generation methods to choose from, which are explained in further detail in the paper. Then, we filter out any labels that are deemed to be low quality. For reference, we define a label to be low quality if it has high error under the ground truth dynamics. After adding these generated labels to the demonstration dataset, we can fit a policy to the data using your favorite imitation learning method, which will enjoy better performance due to less deviation from the expert demonstrations. For simplicity, we used behavior cloning in our experiments. It's important to note that these generated labels are not necessarily optimal under the expert's objective, since we have no notion of optimality in this problem setting other than the provided demonstrations. However, since they guide the policy to remain close to the expert data, they still result in a performance boost and increase in data efficiency. As I mentioned, the generated labels have provably bounded error under the ground truth dynamics. That is, we can metricize how correct they are. This prevents us from hallucinating infeasible and meaningless transitions, which would impair policy learning. This inequality governs the bound on the label error, so let's break it down. First, let's just define label error. The label error is the accuracy of the generated label under the ground truth dynamics. In other words, a label has a low error if the learned dynamics model predicts the same state transition as the ground truth. The upper bound on this label error has two terms, the first of which is the model error. This is simply the training error of the learned dynamics model on the demonstration data point that the synthetic label was generated from. Since the model was fit until convergence, this is negligible in practice. The second and more important of the two terms is the continuity term. I mentioned that we exploit local continuity in the dynamics, and this is where that happens. By assuming the environment is locally Lipschitz continuous, we know that the difference between the learned and ground truth dynamics, or the label error, is at most the label distance multiplied by the continuity factors. Here, K1 and K2 are the local Lipschitz coefficients of the learned and ground truth dynamics models. The original paper filters on label distance as a proxy for label error, but in this work we refine this filtering algorithm. We show that we can approximate these continuity factors by leveraging the Jacobian of the learned dynamics, allowing us to directly use this error bound to filter out high error labels. In practice, we define a maximum allowable label error, which constructs a trust region around each data point. By throwing away all generated labels outside of the trust region, we can maintain confidence in the accuracy of our labels. What's cool about these trust regions is that they implicitly uncover the underlying dynamics regimes in this task and environment. We illustrate this with a representative trajectory from our cube grasping task. The size of these circles indicate the size of the corresponding trust region, and the green circles correspond to states where the robot is grasping the cube. We see that the trust regions are much bigger during free space motion, which is very continuous. However, as it slides along the platform on the bottom and grasps the cube, the trust regions are very small, indicating that the environment is much more discontinuous in that region due to the contact dynamics, which makes it harder to predict the dynamics further away from the demonstration data. Let's look a little deeper at this trajectory. The x-axis of this plot is the label distance, or how far a generated label is from the ground truth data it was generated from, and the y-axis is the local Lipschitz constant at that point. We see that the data points actually cluster in a semantically meaningful way, separating the green points, the states where the robot is mid-grasp, from the rest of the trajectory due to the difference in continuity and distance. Additionally, note that the x and y axes are the two factors that comprise the continuity term of the label error bound, and so their product corresponds to label error. So, the dashed lines represent different label error thresholds used for filtering, and we see that they segregate out high error data that would damage policy performance, confirming our design of the filtering algorithm. Now here's the fun part. Does it actually work in the real world? These are the three fine manipulation tasks we study, in increasing order of difficulty. The first task is grasping a small 1 centimeter cube, and while it's the easiest, it is still non-trivial due to the small size and very light weight, making it very susceptible to disturbances. The second task is inserting a gear into a windmill mechanism, where the axle is 5 millimeters thick and must be inserted into a tight fit with a gap of less than a millimeter, requiring very precise insertion. The third and most difficult task is picking up a coin off a table. The coin is only 3 millimeters thick, and along with its round shape and slick surface, make it very difficult to grasp. We ablate across the proportion of data used to train a policy, and we see that CCIL especially shines in low data regimes. In the cube task, with just 20% of the dataset, we see a substantial boost in performance, and across the board we still see a performance boost with our data augmentation method. We also observe that CCIL improves the robustness of the resulting policies to external disturbances. The expanded data coverage helps the policy recover when forcibly moved further from the data support of the expert demonstrations. While it shows promising ability to improve data efficiency and performance in real-world imitation learning, our work is not without limitations, which opens up exciting new avenues for future research. First, we see that there is a clear trade-off between the usefulness and correctness of the late-correct generated labels. As proven in our theoretical bound, a small label error threshold will result in more accurate labels, but they will necessarily be closer to the expert data, resulting in a smaller increase in data coverage, which means the data is therefore less useful. If the label error threshold is too high, however, then the labels might be more useful since they increase coverage the most, but they're not necessarily accurate. This phenomenon is illustrated in the figure on the right, where we ablate across our label error threshold. A threshold of 0 results in no generated labels and exactly recovers vanilla behavior cloning, while a very high threshold incorporates low-quality labels and degrades policy performance. Empirically, we see that in the middle there are strong and robust peaks in performance, but it's difficult to predict where these peaks may be, or even how many there are. By extending our theoretical framework to tackle this problem, practitioners can have a much higher degree of confidence when deploying this method. Additionally, the use of continuity requires access to low-dimensional state, since state spaces like images are very sparse and discontinuous. Future work could overcome this problem by learning a latent representation suitable for continuous dynamics prediction, which would allow our observed efficiency and performance gains to translate to many new tasks and environments. Thank you for your time, and I hope you enjoyed hearing about our work.